Okay, hello. So thanks for everyone for turning up today. So I'm just going to introduce our speakers today. A bit of housekeeping at the start. So we'll be recording this and sharing this on YouTube shortly after. If everyone could keep their camera and their microphones off, so we could focus on the presentation, and then just put them in the chat, and we'll come to those right at the end. So. Once again, hello to everybody. So I'm Stephen Haben, a data science consultant at the Energy Systems Catapult. And this is another Value in Energy Data seminar, webinar, where we try and demonstrate sort of the uses of data and digital in the energy sector. So I'm very pleased today to have our two speakers, both from the Smith Institute, Ruth Voisey and Kieran Kalair. Just a little bit about both of them, and then they'll start their talk. So Ruth is Technical Director and Head of Innovation Strategy at the Smith Institute. She specializes in developing new proactive solutions to some of the biggest challenges facing their clients at the Smith Institute. Ruth is currently developing solutions that can enable businesses to adapt to climate change and future-proof their business operations through the next decade and beyond. Kieran is a senior mathematical consultant at the Smith Institute and specializes in using data analysis, explainable machine learning, forecasting, and other techniques to deliver actionable insights to decision makers. In recent projects, Kieran has collaborated with a distribution network operator to use explainable machine learning to support vulnerable customers, and with the energy system operator to enable a more dynamic reserve setting process. So with that, I'm very pleased to introduce Ruth and Kieran, who are going to be talking about putting data to work, getting projects over the line and into use. So Ruth, I'll let you take it away. Thank you.
Great, thank you. Can everyone see the slides all right now?
Yeah, I can see those.
Great. Nice to be here. Thank you very much for having us, Stephen. So yeah, we won't go into the title and the introductions too much because Stephen's just done a great job, but here we are, so you can tell the difference between me and Kieran as we speak. But yeah, I've been at the Smith Institute for a couple of years, and before that I was actually working at Dyson in machine learning research there on intelligent control systems. Kieran, do you want to say hi as well?
Hi there, everyone. So I've also been at Smith Institute for just over 2 years now. Before that, I did a PhD in transportation modelling, so essentially maths and data science applied to road traffic. But since joining, lots of involvement in different energy projects.
So we're really happy to be here with you all today. But before we get stuck into kind of our key takeaways for getting projects over the line, we thought we'd tell you a bit about the Smith Institute. So what is the Smith Institute? We're an award-winning team of mathematicians, data scientists, and innovators. Depending on who we're speaking to, sometimes we say, you know, we're applied mathematicians, and people don't know what that means, maybe, or industrial mathematicians, don't know what that means, maybe. Problem solvers, super geeks, I don't know. We're trying a few different things, but what we're really about is solving complex problems using different technologies and techniques to try and find the best solutions and have the greatest impact. The award that we've won is the Queen's Award. That is for some of the work that we've been doing in spectrum auctions, where we've worked on over 30 auctions across 10 countries, generating over £100 billion worth of spectrum licenses. And so that was an award that we received a few years ago. We're also a Garobi partner, and we were the UK's first partner there for their optimization software. So we work across many different sectors. Energy forms one of the largest of the sectors that we work in, but we also do work across security and defence, fast-moving consumer goods, transport, spectrum and space. And we're not limited by these, you know, we dabble in other areas as well, as and when we need. And we use kind of the transferable skills that we have in mathematics, data science and AI to solve problems across these different sectors. And where we're trying to use our skills is to have this great impact. So we're wanting to be able to impact our clients and the work that they're doing within society, economy, and the environment. This is our mission statement, and it's really embedded in our core values as a team as well. And this impact part is really where we're focusing again on the talk today about how do you get something from that proof of concept integrated into our clients' systems and decision making on a day-to-day basis in their business as usual. And this is quite a challenge, but something that we do kind of on a day-to-day basis. We kind of sit in this unique position between academia and industry. A lot of our technical team come in with PhDs and postgraduate experience. And we still have a scientific board as well, which is lots of people from different academic institutes across the country. But we're working on how to take the techniques and technologies that are being developed in academia and how to get them applied and working within industry. So what do we really mean by that previous slide in terms of impact? What sort of impact do we have? We support people in their decision making, so using evidence that's driven by data to inform that decision making and make sure that that's intelligent. We enable customers to give improved services to their clients. We give deeper insights in terms of behaviours or expected things to happen in the future. We support a lot of businesses in their own innovation programs, as well as having our own internal innovation work. So there we're using kind of our experience in horizon scanning to support them on their expansion into AI or quantum, for example. We support clients in their operational efficiency, trying to make things run leaner, greener, cheaper, etc. And we give greater confidence for the future. So we look at a lot of what has been happening historically, what's happening now, but we also help our clients to look at what might happen in the future and how to be resilient against the changes that we might see. And so what our clients actually get is this confidence that the decisions that they're making in uncertain times right now and in uncertain times in the future are backed up by data, evidence, and that rigorous thinking. This quote here is a quote that one of our clients gave to our CEO, Heather, where they said simply, "You help me sleep at night. Thank you very much." So some specifics. In the energy sector, we've got a few projects that we have ongoing and have worked on in the past. So one with EDF Energy, where we've been looking at modelling the graphite cores and looking at the safe delivery of low carbon energy there. There's been a few projects with National Grid ESO in the past and at the moment as well. A couple of those have been around managing uncertainty to forecast supply and demand, which Kieran has been working on, so may talk a little bit about in terms of some use cases later. And also modernising the optimization algorithms for the control room. So in the balancing, how can we take the legacy algorithms and get them ready for the future and then changes that are coming. Outside the energy sector, some example projects that we've been working on are with Inmarsat, looking at satellite communications and optimization there. With Coca-Cola, looking at the forecasting there for their sales and demand, so understanding when there's weather events, how that's going to impact their sales and how they should be prepared for that. And with a UK rail company as well, we worked with them to show them the benefit of machine learning, working on a proof of concept, which was able to give them some kind of expected returns if they invested further in their machine learning. And that then gave them the business case, which they could use to invest in developing their own team. So we actually then worked with them to recruit and upskill their team so that they were able to take that proof of concept forward alongside other ideas that they had in machine learning and AI. So because we see a lot of clients in many different sectors, we have a good viewpoint of the problems that are facing different organisations and also picking out these common themes. So towards the end of last year, I worked with Tech UK and sat on a steering group for AI adoption and fed into their report and their research with some of the insight that we see in the problems that organisations are facing. And these were some of the key points that we pulled out and that were gathered through the input from others as well. So first and foremost, a real AI skills gap, and it's really imbalanced as well between different sectors, or even within one sector, there's a real imbalance from some organisations to another. So some organizations have no skills in AI at all, but know that they need to use it to, exploit the most of the data that they have. Some organizations have some skills, but maybe not buy-in at a senior level, etc. So there's a lot of work to do to try and get everyone on a level playing field, and complementing the AI skills with also the kind of applied skills, knowing more about the domain that you're working in and how to get things across the line. There's a real lack of trust in AI from people that may have to use the outputs, even sometimes for the people that are using the AI systems themselves. And so that's something that we need to work on, and provide some trustworthiness with our models to build that. There's a limiting organizational culture and understanding. So you get that at kind of both ends of the spectrum, from senior management saying we need to use AI, but I don't really know what it is, through to I don't see the benefit of using AI, machine learning. And with that comes kind of seeing through the hype. So if it is on that side of the spectrum where people are saying, oh, yeah, let's just jump on this AI bandwagon if everyone else is using it, we need to really understand how and why you need to use AI. And then on kind of more of a technical front, there's a real challenge in data quality and accessibility, and that's very inconsistent across sectors and intersector as well. And then the infrastructure that businesses need to use to enable the deployment can sometimes be challenging if you're working with like a legacy or very complex system as well. When we're working on data science, machine learning, mathematics project development, we have this sort of life cycle that we follow that moves from the steps of prepare, design, build, deliver, and partnership. And throughout that, we offer support all the way through. And what we see is that historically, businesses that we've worked with have struggled at different parts of this kind of diagram and at the different stages. And it makes, therefore, that final delivery and business as usual integration very challenging. There's a lot out there in terms of blogs, papers, training on the build aspect. If you want to use an SVM, how do you go about getting your data ready? How do you build it? How do you test it, etc. But there's very little around the other steps, and these are so important. I'm not going to talk into the detail right now of where we've seen failings in these different steps, and instead I'll hand over to Kieran, who's going to take you through some of his highlights. All right.
Okay, cool. I've got control. So thanks. So yeah, I'm going to just generally talk through some of the things we're thinking about and taking account of when we're actually getting started on one of these data science projects, or partway through it, or getting towards the end of it, and how at each step on this diagram on screen there are choices you make that can have quite significant impacts onto the practicality of what you produce and the usability and how long it will last. So one of the first things we have to always do, because we work across different sectors, different companies, different applications, is understand the macro challenge. And by this, we essentially mean when we're solving a problem, are we addressing a symptom of some larger problem, or are we truly targeting the original issue that should be solved here? So you might say something like, we need better forecasts of X, whatever that is. But rather than just say, okay, let's build a model to forecast X, we should really sort of take a step back and say, well, okay, why do you need better forecasts of this thing? Why are you forecasting in the first place? What do they feed into? And is it something further up or further down the line that's really the issue that's causing this that might be worth solving instead? And you can very quickly go into, I guess, sort of rabbit holes or very fixed mindsets where you try and optimize a model that produces brilliant forecasts of something, but in doing so, you might lose sight of the overall goal. You can spend years refining a model, but the actual benefits you get are obviously going to diminish over time, because at some point a solution is good enough that you can use it for what you need to use it and refine it slightly, but the macro challenge is still going to be there. And when we think about predictions or models, before we actually attempt to build anything, we should be thinking about what are the inputs, not only inputs to the model, so like features or what you might call them, but inputs to the entire process overall. You know, what is driving this process that we're modeling here? Is it human interactions? Is it part of just an automated system? You know, are there errors that we can model or errors that are truly random, and how do they impact our choices on how we're going to solve it? And, you know, one of the things we commonly see in all sorts of applications is that rules of thumb have become standard, and people have ways of working that they trust and have agreed over many, many years, and they aren't going to go away overnight. So how can you incorporate these sorts of ideas, this expert knowledge, into what you do and validate or invalidate some parts of it? And ultimately, whatever you build, there's very often going to be a human somewhere in the loop, either using the output, or, you know, your output might be advice to a human, or perhaps it is a fully automated system, but somewhere along the line a human will take an action or see the result. And do you understand from the outset where the human fits in and what they want to see and what they want to do with what you produce? And ultimately, if you design the dream data pipeline and modeling pipeline that will automate everything, track all your scores, is it actually practical in the time you've got and with the resources you've got? And will people actually trust it? You know, you could spend years developing something, but if you don't truly understand who's going to be using it and why, practical use is going to be extremely limited. So generally, we spend quite a lot of time understanding the larger problems before we dive into the very, very specific problems that we're trying to solve. And after understanding the large problem, a big step we do then is say, okay, we've settled on a problem to solve, or maybe a set of problems to solve. How do we formulate those in a mathematical or statistical sense? So here we want to really distill what are often incredibly complex problems that have enormous amounts of variability and influences and things that will change their behavior into a solid mathematical problem that you can state and you can model. And in doing this, you're implicitly making decisions. What am I going to leave out? What am I going to include? How am I going to encode certain things? You know, perhaps an expert says, on windy days, I always have to do this. Well, okay, how am I going to write down mathematically that there's an influence there? Am I just going to have wind speed as a feature in my model, or do I want something more explicit? And part of doing that is to say, well, okay, what scenarios will this solution be used in? And does my formulation cover that? So if my formulation is great at modeling windy days, but does not work at all in the summer or something like that, why are we doing that? Do we truly understand how the formulation relates to the practical use? And obviously there's going to be stakeholders at all sorts of levels with all sorts of understanding. And do each of them fully buy in to what we've agreed to solve and how we've agreed to solve it? If you go and ask 10 different people who are involved in a project, what do you think the output of this project is going to be? They might give you 5 different answers. And does your problem formulation cover all of those in a sensible way? And that can be a very, very hard thing to come up with, because sometimes these formulations themselves, well, not the formulations, but the things people expect to get out could be incredibly vague, or perhaps, you know, they want everything without fully understanding the limitations of your data and your models and things like that. A good example of where we do this is when we work on the dynamic reserve setting projects. It's something we've been doing for a couple of years now. We're not just building one model. So the problem formulation there was users will need to run models multiple times each day at different time scales, at different time points, to prepare different things. They might want some long-term advice and then some much shorter-term advice. So we're not just building a single model that will predict reserve requirements. Instead, we're building a suite of models and a pipeline to go with it that solves a series of problems, and essentially the different stakeholders, the people doing the long-term planning, the people doing the short-term planning, and the people doing something in between, all have their needs met. It's not just a simple modeling exercise. There's quite a lot more to it when you dig into the formulation. So suppose we've understood our challenge and we formulated a way to express it mathematically. Before we then actually go and make anything, we need to sort of think about system architecture. And this links heavily with this practicality and designing an approach. But there's sort of two extremes we can do here. One is to say we've got a legacy system and we're just going to fully embrace the world of AI and data science and we're going to throw away everything and start again. Or, and what's probably much more common, is to say we have some enormous complex system, there's loads of moving parts and there's various things we do right now to solve it, and we need to take a piece of this, some piece of the much larger puzzle, and we want to improve how that piece works. We want to build a model that does one part of a very complicated process better. And going for the first thing could obviously in the very long term be very valuable. However, it is an enormous gamble and you need to make sure that at some point along the way you can actually join these things up. So you can swap from the old system to the new system and everything's verified and people understand what's going on. A lot of what we do is in creating something that's adaptable, that will slot into existing processes somewhere. And when we're doing that, it's always very important to say, well, is what we're designing actually going to meet the requirements of everything before it and after it in this modeling pipeline? So these could be really simple things like how often does this thing need to be run and produce an output, and can it do that? Or it could be that somewhere down the line someone's working at a 30-minute resolution where they need a prediction every 30 minutes that does something. Does our model adhere to that, or does it need a coarser or finer grainer solution? And do we then have a way to map from our output to what that person needs in some sensible, justified way? And really understanding what's going on even slightly further down than what we're modeling is quite important in that, and exactly how that impacts our choices. There's a lot of temptation if you were to sort of browse the literature to build the best possible model, but best here is not quite a well-defined term very often. Best here is the one that achieves a very good error metric, but also fits into an existing architecture, produces something you can actually use and people will trust and will be part of a wider puzzle very often. And one thing that personally I think is one of the most important things we do is consider methods versus requirements. So we're all well aware that there's an enormous amount of AI hype right now, machine learning hype and whatnot. And in some instances, it's justified. AI and machine learning are great at all sorts of different things. However, they're not perfect for everything. And are we trying to solve a problem with a specific tool, or are we trying to solve a problem and we're open to choosing the best tool for that? So very often we could be tricked into thinking, oh, AI is great, it's going to solve all our problems, so let's just throw the neural network hammer at everything and it might work. Now, the issue with that is if we just go in with a methodology and try to solve every problem with it, we're ignoring quite fundamental choices that you can make. So what's your data quality look like? How much of it do you have? How much of it's missing or incomplete? If you have lots and lots of data and it's all perfect, then yeah, maybe AI is what you need. If you don't, there's a whole wealth, there's hundreds of years of Bayesian statistics that might be more appropriate for this sort of problem. If you're trying to forecast something, there's equally hundreds or thousands of years of time series analysis work. Is that something we should turn to, or do we need ML? And do we understand the distinction of why I'm choosing one tool over the other? Equally, if I'm using some sort of classification problem, is logistic regression enough? Do I need a neural network? Why am I choosing to do this? And making conscious decisions around these is very important to really understand, why am I doing what I'm doing? What do I expect to get out? And do I understand the underlying problem here? And obviously with any of these choices, it's a trade-off between the complexity of the model, the computing power required to do it, and the assumptions that it's going to make. If I'm assuming all my data is going to be perfect and present indefinitely, then machine learning probably is the way to go. If I know there's an enormous amount of noise, classic statistics probably has some answers too. But ultimately, the one thing I always bang on about for every single project we do is let's think about the methodology and not just use something we've used before that has worked well, but say every distinct project should be considered, what is the right thing to do here, and can we justify why we're doing that? That's not just, I've used it before and it worked, so let's try it again. Now, obviously, every AI/machine learning talk you go to, someone probably talks about data, and we say, oh, big data's everywhere, and we're all going to use it to do great things. And that's true in some sense. However, I sort of think of this as a scale. So you have some problems where you've got no data or very, very little data. It's so expensive to collect it that you're never really going to have sufficient data sets to build neural networks and things like that. And then on some other side, you have sort of the entire data you could possibly collect if we set up all sorts of processing pipelines that scrape social media, the websites, sensor data, all that sort of things. And you actually have to ask yourself at both ends of that scale, what is relevant here and what should I use? So if I build a pipeline that uses some data to model, is this data pipeline actually in production? If I was to run it every single day, will it be able to execute in real time, repeatably, reliably? Will any of these data sources suddenly stop reporting, or are any of them perhaps intermittently available? And understanding that, essentially building your model on a solid foundation is quite important. Now, for the reserve setting example we talked about earlier, we're using all sorts of different data sets for that, but they are all ones that we know for a very long time, and for a very long time in the future, they are going to be present, they're robustly handled, there's lots of error checking that goes on. So we can confidently say, here is a pipeline, it's built on these data sets, and for each of them, we have fully understood when they're going to be available, how often they're available, their uptime, things like that. But obviously, there are lots of applications where that's not quite so clear. Perhaps you're scraping public data, and will the website change its API terms? All of a sudden, your data becomes unavailable. And there could be other questions, for example, quality. If I build a proof of concept on some historic dump of data, would the quality I get of data in real time match that? Or has it been somehow augmented, corrected, changed to fit this proof of concept? And can I automate the process or the steps that were done there? If a human sat through and looked through all of it to correct it, I'm never going to be able to automate that to the same degree in real time. So when you're building proof of concepts with sort of one-off data dumps, it's very important to say, how confident am I that I could truly recreate something of this kind of data quality? And obviously, big data, there's lots of it. Can I actually run my pipeline in the time it will take to create a usable result? If my model runs once a day and it takes 2 days to process the data, well, then all of a sudden I can't make so many up-to-date current predictions because I'm just waiting for the data to churn. And an increasingly relevant point here, particularly with the work we did with the DNO on energy vulnerability, is what biases are there in my data, and are they constant through time? If I'm collecting, data relating to humans, are certain groups underreported or completely missing? And what are we going to do about that? And how does that affect my models? If I've got an explainable model that relies on demographic data that is biased, well, my explanations are now going to implicitly have a bias in them because of that. And do I fully understand where that's coming from and why? But ultimately, the real point here is think about both having too much and too little data, and audit what you've got for biases, reproducibility, real-time access, things like that. So now we're finally on to building models, but build them with care, because I suppose I follow some tutorial. There's many out there in different academic sources, and they'll say, okay, we're going to get a model and it's going to optimize an error metric, the accuracy, the precision, the recall, the mean square error, something like that. But the best model in a practical operational scenario is not necessarily the best model in terms of that error metric. So I could have 10 candidate models and they could have varying error scores. Lower is better. And the classic thing to do would be to pick the model with lowest error. And that would be my best model in some sense. But if you take a step back and you say, well, okay, what does a good model look like to each of the stakeholders here? Wow, very few of them probably think of that error metric as their measure for good. So of these candidate models I've got, how interpretable are each of them? And how much computing power and memory and whatnot do they each take to run? You know, do I say for a 1% increase in accuracy, go and stick a GPU farm somewhere and call it every day? You know, that is perhaps an extreme example, but things along those lines could be real choices. And if you think about the larger processes, if I spend 6 months getting a 1% improvement in my model and it takes 3 times longer to run, which of my users actually find that a good use of time, a good use of effort? Whereas we could be doing all sorts of other things to improve this process that might see much better returns. And sort of the point of this entire slide and this entire section is that a good model in a mathematical sense minimizes error. A good model in a practical sense suits each of the stakeholders' needs. And it can be extremely hard to align those two things because it might be very hard to phrase stakeholders' needs mathematically, and it might be very hard to phrase the mathematical optimization in an easy to understand way for different stakeholders at different levels. But I would say that it's so rare for people to talk about what does an optimal model look like without just saying it's got a good F1 score or it's got a good accuracy. In a couple of the projects we've been working on, so one of them was classification based. So we had images and we built a classifier from them. And you might say, okay, the optimal model balances precision and recall, and you tune it until you're happy. But in this example, the customer was more interested in getting sort of alerts when we were very confident that a particular feature was present. So all of a sudden, we don't equally account for precision and recall. The objective that they're interested in has a higher weighting on one of those two factors. And that's quite a subtle thing to include in your model fitting procedure. But it's something that in practice, someone using it might say, oh yes, whenever that model flags something up, 99% of the time, it's something I do need to look at. Whereas if we hadn't have done that, perhaps we'd flag things up and people would just have come away thinking, oh yeah, half the time that model, it sort of flags up things, but I didn't really need to check it. It's a waste of time, things like that. So it's very simple tweaks to make something that turns out to be quite a big gain in terms of trust. And one of the final points, so I'm particularly interested in machine learning explainability, both from an academic sense and from an applied sense. And in using this in practice, what I've come to find is that there's almost 2 layers to machine learning explainability. One is I've got a black box model, I need to explain it. And the second is I've got my explanations, I now need to explain them and how to use and interpret them to users. So when I talk about explainability, there's sort of a human aspect and a mathematical aspect. If I'm making a support system or decision support, something like that, at some point a human's in the loop, and at some point they may or may not want to say, why is my model telling me to do this? So we could choose one of many, many ways to explain a machine learning model. And firstly, we have to choose a way that they'll understand. And secondly, we have to then say, what exactly can and can't you do with these explanations? So in a different project I was working on, we had the contributions from weather to a certain prediction output. And the users would, it was fully explainable. We computed contributions per feature to the model output. And then when people started to use these, they would come to us and say things like, oh, so because the wind contributes 100, does that mean if I think it's not going to be windy, I can take 100 off the final answer? And the answer was no, because the way these are computed is very specific, assuming certain things about the properties of the inputs in the model. So understanding how humans are going to use these explanations and then informing them of how to use them correctly is sort of a two-stage process here. And obviously, trust, why should I trust you? There was a provocatively named paper actually called "Why Should I Trust You" in the machine learning literature. But ultimately, yeah, what exactly do we want from our model? We want it to be used. We want people to start adopting it, and we want it to ultimately save, money, time, emissions, something like that. And the only way that's ever going to happen is if the end user is actually convinced they can trust it and use it, and it's better than their rule of thumb or their baseline right now. And part of this buy-in is not just the people who use it every day, but the perhaps stakeholders who are aware this is happening but don't see its output all the time. And if they fully understand, okay, we've got this thing, it explains exactly what's going on, they may be more inclined to support it than if they just have some black box. And of course, reputation. Do we, as modelers, have full confidence that our extremely nonlinear, complicated model is capturing exactly what we're saying it is? Do we know why? Well, do we know what's driving these very complicated relationships that we're modeling? And ultimately, in doing that, you can understand a lot more about your problem. So one method of model refinement is to build a model, look at explanations as to why it's doing what it's doing, and then take that and some expert knowledge and say, well, okay, I can now refine my model because I'm fully aware that it's underrepresenting this aspect, or it's too reliant on this aspect. And when I speak to experts, I know there's something fundamentally different going on here. So machine learning explainability is partly, let's build trust, let's get people on our side. But it's also partly, as a modeler, what can I do to improve it? And the ultimate question we're trying to answer here is, why is my extremely complicated, nonlinear, highly optimized model doing what it's doing? And that's both answer to someone who's using it, who doesn't care that it's got 50 billion parameters and took 2 days to train, or us who are saying, how can I make my model better? And I think often people talk about explainability and they just mean the first. But the second part is a very, very valid way to address model building. And I think it's back over to you now, Ruth.
Okay, just trying to turn the slide over to the next one. It's being a bit slow. Okay, so to summarize everything Kieran's just explained so amazingly, thank you, Kieran. I've put our kind of timeline of our process here on the right to remind you of our stages of prepare, design, build, deliver, and partnership. And I think the points that Kieran's just raised kind of fit into these. So we do a lot of work early on in this preparation stage. So understanding that macro challenge is something that we have to do really early on to make sure we've got a good handle of what we're about to embark on. Problem formulation also sits up here at this early stage. Understanding the current process and practical considerations, you kind of getting that understanding at that preparation stage, and then as you move into the design stage to understand what is your new system architecture going to be like, what sort of modeling approaches might you be exploring, feeds into here. This is when, yeah, your best method comes in after everything that you've done before and before you really embark on that build stage. At this build stage and design stage, you need to be building not just the model, but this pipeline that Kieran mentioned. So you know that you're going to be able to have this data feeding into your model reliably as you move into productionization. And this point about what optimal model looks like to you, obviously this is the output of your model, but I do think that this is something that does need to be considered at this early stage. But it's the fun part that you get out once you've done some building and you start to iterate your model there. And the explainability, again, this is all about output here, but it's something that needs to be considered at this early stage when you're preparing and designing. Because if you know that you're going to need these explanations and they need to be in a certain way, then that's going to affect the types of modelling that you would want to do. But it's definitely more of this output. So that's everything from us today. We've left some time so that we can have a bit of a Q&A. So if there's any questions that you have, please do ask, and Kieran and myself will try and field them.
Brilliant. Thank you very much, Ruth and Kieran. That was really good. It was great, accessible sort of overview of sort of practical ways of applying database projects, really. Yeah, so please put your questions in the chat. I have a question actually, which is, I guess this process you're going from, designing and then sort of implementing. I guess at the end you sort of have some tools which you have to hand over to the client. One of the challenges it seems to be with sort of data science projects is often they're sort of implemented, they do a really good job, and then often you're handing it over to maybe those who haven't got the skills, because that's often why they've outsourced this, I guess. So I'd like to understand maybe some of your challenges, but maybe some of your solutions of how you go from here's the tool and how to make sure it gets implemented operationally in practice, so you get the most value out of it, I guess.
Yeah, absolutely. So every client that we work with has a different technical capacity themselves, and so when we're at that prepare stage, we really account for that, and we define at the start what is the end solution going to look like, what's technology readiness level do we need to get to. Is this a model that we're going to develop for you and release a report that gives you some insight? In which case, we don't need to be integrating this into your AWS architecture, etc. Or is it something that you need to fit into your legacy system and you have some technical capacity to support us in that, or you have zero? So we really call that out early on. And then as we're working through the different stages, we work really collaboratively with our clients as well, so that as we're developing things, they understand what we're doing and why we're doing, and so that there's that kind of constant knowledge exchange. And it's two-way as well, right? Because we're working with domain experts that are really specialized in their areas, and so we want to account for that when we're building any models to make sure that we're understanding the nuance of some of the data, or the kind of likelihood of some of the outputs. And so then when we get to this endpoint, we're on the same page of, okay, this is the sort of resolution that you wanted at, and we have kind of a transition period depending on what their technical capacity is. Kieran, is there anything you want to add?
Just that it's definitely most successful when there's a very clear collaborative team at SI and team at customer working together throughout the project. So they understand the code base, so they understand the intricacies of the modeling, so they understand why we've done what we've done and where it all fits together. So yeah, I think even if we're not giving over code in a given month, getting that relationship started and making sure it's more like a single team is really the key to getting that to work.
Brilliant. Thank you very much. And a second question, I guess you mentioned before that you sort of you assess the landscape a little bit about what tools that you may be useful. I guess there's a lot of hype around. I guess the question is, you've obviously ChatGPT has become very sort of popular, and a lot of people want to jump on that and maybe sort of implement it. So a quick question really about how do you evaluate which tools maybe you think will be useful, which won't? How do you sort of separate the sort of hype for the practicality and those elements?
There's a few different things that we consider there. So a lot is based on our personal experience, technical and kind of applied in the different sectors and areas. We'll also look at, we are always horizon scanning, looking at new technologies, and we'll be looking at kind of the technical suitability of those, but we'll also be looking at kind of the security of those as well, understanding how they adhere to our security policy, but as well working with the clients to understand how that might adhere to their security policy, and whether it's suitable to use certain new tools or not. And then if there's something that is more novel to us, then we would always build in time in the early stage of the project to be doing a literature review and making sure that we know all of the different methods that could be applied in this particular area.
I think part
Brilliant.
of
Kieran, sorry.
from a sort of when we're actually starting the project, I'm always sort of asking myself, regardless of the hype, why would I use a given method? And that could be, okay, it's very accurate when this sort of thing's true, or it handles missing data very well, things like that. And always sort of keeping options open to try and give this objective view of what has led to a given model choice. And yeah, I think it would be extremely risky to start off by saying, okay, ChatGPT, that's what we're going to use, let's go, rather than doing this pre-assessment of what are my tools and why. Yeah.
Brilliant. Well, thank you very much. So if there's no more questions, then I guess we'll finish there. I'll just I put the link in for the YouTube channel, so this will be uploaded there shortly after that. So, but I want to give a big thank you to Ruth and Kieran again for the really interesting talk. And Ruth, you're up for being contacted if you have any. Well, so you put your address on there, so please contact Ruth and Kieran if you have any further questions. And yeah, just one last thing is, yes, thank you very much, and speak to you soon.
Yeah, thank you so much for having us.
Thank you.
Thank you. Cheers.
Bye.